Finite transient diffusion problems are a very important topic to understand when working with or when studying mass transfer. And in this example, what we will be analyzing is how to model the concentration of phosphorus as it diffuses into a cylinder of silicon. And this is a common practice in the semiconductor industry, in which engineers are tasked with figuring out how to dope silicon wafers to precise levels in order to create integrated circuits and microprocessors. And to start off with, the system that we will be analyzing is a long cylinder of silicon, and around this cylinder we will have some kind of phosphorus gas. And over time, this phosphorus gas will diffuse into our cylinder. And if we were to examine what the concentration profile looks like over time inside of our cylinder, what we will see, I'll draw this over here to make things easier to follow. I don't know why I draw this way. At r equals 0, and this point will be r, and this point will also be, we'll call this point capital R. And the y-axis in this case will be Ca, the concentration of phosphorus in our silicon wafer or cylinder. It will be equal to, at the surface, a constant value Cas, and at time equals 0, it will be equal to some value Ca0. So if we took a snapshot of the concentration profile right when we started diffusing phosphorus in, we would have something that looks a bit like this. And this is a little poorly drawn, but you get the idea. And then as time goes on, what we would have is a concentration profile that evolves like this. And if I could draw well, this would be symmetric. And so as time continues, we eventually reach a point at which we have a uniform concentration of phosphorus inside of our silicon cylinder. And at that point, we no longer diffuse because there's no gradient. And the way we begin these problems is with the we go to our definition of the flux vector, NA. And NA tells us that the molar ratio, the negative molar ratio of your component A times the diffusion coefficient of A into B, the diffusion coefficient of phosphorus into our silicon wafer, times the gradient of your concentration plus the velocity vector times the concentration of A inside of your system must be equal to your flux vector. And so something to note at this point is that the gradient of a scalar is a vector. And this is a side note, so the gradient of C is equal to, and because we are working in cylindrical coordinates, it will be equal to dc dr, the partial derivative of your concentration in the r direction, times your radial vector, plus 1 over r dc d phi, the partial derivative of your concentration vector in phi, times the phi unit vector, plus dc dz times the z unit vector. And to begin these problems, what we would first note is that the concentration profile inside of our cylinder, C, is equal to a function of R only. And because of that, because C is not a function of phi or z, we can cancel these terms out right here, and we are left with the gradient of C must be equal to dc dr times the radial vector, the radial unit vector. And just to clarify, in this flux vector equation, every term inside must also be a vector. So because YA and DAB are scalars, the gradient of a scalar must be a vector to make this equation agree. And so the next step in modeling this system will be to go to the mole balance equation, which tells us that the divergence of the flux vector that we just evaluated plus dCA dt, the change in the concentration of A with respect to time, minus the rate of reaction must be equal to 0. And in this problem, we can assume that there's no reaction occurring, therefore it's equal to 0. However, this term does not equal 0 anymore because we are working with a transient problem. Transient. And the next step here, if we plug in what we found for the definition of our flux vector, what we would have is that the divergence of flux vector will be equivalent to the divergence of minus YA times DAB, the diffusion coefficient, times the gradient of your concentration, plus the molar average velocity times CA, and we already went over that we can cancel this term out. If we note that the molar ratio of A and the diffusion coefficients are constant, we can pull these out, and what we have tells us that minus YA times DAB times the Laplacian of your concentration is equal to the divergence of your flux vector. And at this point, I would like to take a moment to discuss this Laplacian quantity here. And I know that I already simplified the gradient of our concentration, but if we kept things generic, so we can apply this to other examples, what we would have, so this del squared times C, the Laplacian of C, is sometimes also written like this. This is the Laplacian operator. This term in cylindrical coordinates is equivalent to 1 over r, partial derivative with respect to r, of r dc dr, plus 1 over r squared times the second partial derivative of your concentration with respect to phi, plus, and then the partial derivative of, or the second partial derivative of your concentration with respect to z. And because we established previously that c was not equal to a function of phi or z, we can cancel out these last two terms, and what we are left with now is the divergence of your flux vector is equal to minus YA, the molar ratio of phosphorus in your control volume, times DAB, times, and then 1 over R d dr of R dc dr. And what you'll note now is the this quantity is now a scalar. It is no longer a vector because the divergence of a vector is a scalar. If we now go back to our mole balance in the beginning, what we have is that the divergence of NA vector plus dCA dt must be equal to 0 because we had no reaction occurring. So if we plug in what we found here into this equation, what we have is, and I'm going to add it to the other side to get rid of the negative, the molar ratio of phosphorus in our control volume times the diffusion times 1 over R d dr of R dc dr must be equal to dCA dt. So getting to this point in this model or derivation has allowed us to is a good point to be able to get to, because if we now integrate, we will be able to evaluate what CA is. And the reason transient diffusion problems are more complicated is because CA is no longer a function of just position. CA is a function of the radial component as well as time. And because of this, if we note how we have a second partial derivative with respect to R and a first partial derivative with respect to time, that tells us that we need two boundary conditions for R and one boundary condition for time, t. And looking back at our concentration profile, in which we had something that looked like this, and if we take a snapshot of it at some time, I need to draw better something. What you'll note is how, and this axis is CA as a function of R and time, and this will be at some time t. If we note how the slope at R equals 0 is 0, in other words, dCA dr evaluated at R equals 0 must be 0, this tells us a boundary condition in R. So this is our first boundary condition for R. And then our second boundary condition for R tells us that, and then another thing to note here is that, dCA dr evaluated at R equals 0 must be equal to 0 for all time t, as well as the fact that CA must be equal to CAS at R equals, and we'll call this position big R. So this axis will be little r, and then just to make things more clear, big R represents the total radius of our cylinder. The second boundary condition, oops, sorry about that, my computer likes to crash. I'm in the middle of videos and important things, or somewhat important things. What we'll note here is how at, and I need to change this back to draw, what we will note is how at this point, CAS at R equals big R, and this axis represents our radial component, we are at CAS for all time t. So the first boundary condition was that our concentration profile of A in our radial direction evaluated at R equals 0 must be 0 because it is symmetric for all time t. And then the second boundary condition that we will use in this example tells us that CA evaluated at R equals big R, and at any time t must be equal to CAS. And then the third boundary condition we will use for time tells us that CA evaluated at any R but at time t equals 0 was equal to some initial concentration CA naught. And we can let CA naught equal 0, but to keep things generic, we usually leave it as CA naught. And at this point, because the video is running a little bit long, what I will finish by saying is that what we do now to actually evaluate our integral is separation of variables. And so what we're going to do is we're going to define a variable called big Y. We're going to let big Y be equal to CA, which is a function of radius and time, minus the surface concentration of A divided by CA naught, the initial concentration of A in our silicon cylinder, I'm going to define y to be this quantity, and if we go back to our mole balance, we substitute in y into the mole balance, and that tells us that the partial derivative of y with respect to time, it's equivalent to dca dt, and that had to be equal to dab times the second partial derivative of y with respect to r, the radial component. And at this point, we'll say it's separable. We will assume that y is a separable equation, in which case we can say y will be equal to some function, I should think of, we'll call it r prime of r, and then times some other function big T of some time t, and then we can, with these boundary conditions, rewrite what y is, as well as perform separation of variables to ultimately arrive at what Ca as a function of r and time is. And that's about it. So I'll let the mathematicians out there actually evaluate this. But the main point was setting up this problem and reaching this final result. So let me know if you have any questions, and thanks for watching.